Water leaves a data center as vapor, that is evaporative cooling. Warm water is sprayed into air, heat flying away with the mist. The same trick cools the power plant that made the electricity. Count both, and only 1 part in 8 stayed in the building. This episode is about that arithmetic. Nobody is lying about the water. The answers change because the question does. Where do you put the meter? Start with one careful study. In 2023, researchers priced a single GPT-3 query in water, and they counted it twice, on purpose. Boundary 1, just the building. 2.2 milliliters per query. The water the data center itself evaporates. Boundary 2, the building plus the power plant feeding it. 16.9 milliliters. Same query, same paper, 8 times more. 8 times more from one decision where the count stops. Hold that number. It is the honest heart of the whole fight. Then, in August 2025, Google published its own number, a median Gemini text prompt, 0.26 milliliters, 5 drops, counting Google's own buildings. 5 drops sits far below the older building-only figure. That gap is not about meters. Newer models answer with less computing, and newer cooling wastes less water. 2 years of efficiency. So yes, from 5 drops to a tablespoon is roughly 60 times. But that is 2 gaps stacked, about 8 from the meter, the rest from time and technology. Put the public numbers on one line, each labeled with what it counts. 5 drops, 1 building, newest models. About a tablespoon, building plus power plant, older model. And the viral half-liter, a misreading. The famous bottle of water per email came from dividing wrong. The 500 milliliters in that study covered 20 to 50 queries, not one. A tablespoon is still not much. Remember that. It matters later. So every number is honest. They answer different questions. And the bigger question is waiting one step up the wire. Follow a query's electricity backward, out of the building, up the wire, to wherever it was made. Most American electricity still comes from heat. Gas or nuclear plants boil water into steam, and steam spins the turbines. After the steam has done its work, the plant has to cool down. The cheapest way is the same trick again. Evaporate water into the sky. Count the whole American grid, and one widely used tally lands near 12 gallons withdrawn from rivers and lakes per kilowatt hour. Roughly 1 gallon never comes back. Withdrawn water mostly returns, warmer. The part that never returns, evaporated, is consumption. That is the honest word for water gone for good. Now split the GPT-3 query one more time. 2.2 milliliters evaporated at the data center, 14.7 at the power plants that made its electricity. 7 parts out of 8 behind the fence, invisible to the building's meter. By most published estimates, that ratio holds across the industry. 80% or more of AI's water footprint is indirect, spent on generation, not on racks. Google's 5 drops are measured exactly where Google's responsibility is clearest, its own campuses. The company says so openly. The boundary is printed in the method. Nothing is hidden. The meter simply stands at the fence. Most of the water evaporates on the far side of it. Your 5 drops are real. The rest of the query's water is also real. they sit on different bills. Somewhere miles away, a cooling tower exhales the rest of your query into the sky. That is the answer the headline promised. The data center is not drinking the water, the power plant is. So the fix looks obvious. Stop evaporating, seal the loop. A closed loop keeps the same water circulating, shedding heat through radiators and chillers instead of evaporation. No mist, no loss. Data centers can run this way today. Radiators need fans, and chillers need compressors. Moving heat without evaporation is harder work. The catch is electricity. Evaporative cooling saves roughly 10% of a data center's energy compared with dry systems. Seal the loop, and that 10% comes back onto the bill. Where does the extra electricity come from? A power plant, cooled in most of the country by evaporating water. Run the whole loop on one chart. Minus the mist at the data center, plus more electricity, plus more water at the plant. The savings shrink towards zero and can flip negative. The water does not disappear when you seal the loop. It changes address. Some campuses already pay this premium on purpose, in places where water is the scarcer currency. And there are real exceptions. Grids heavy on wind and solar carry far less water per kilowatt hour. Where the electricity is dry, the loop math changes. But on today's average American grid, the trade stands. Less water at the RECs, more water at the plant. Closing the loop is not a lie either. It is a relocation. Now the last question. The water is spent at the plant, so whose water is it? The RECs and the generation do not have to share a town. Electricity travels well, water does not. A city hosting a data center sees the campus meter. 5 drops a query, counted at the fence. Modest, public, defensible, and true for the question it asks. If that campus draws power from a plant 2 counties away, the evaporation happens there, where that river is. How much and from which river depends on the grid behind each campus. It is checkable, plant by plant. The pattern is the point. The account and the withdrawal sit in different places. And keep the scale honest. One query is drops or a spoonful by any method. The question becomes real at millions of queries, one specific watershed at a time. That is why the argument about milliliters never ends. Each side measures its own question at its own fence. Data centers publish building numbers. Researchers publish grid numbers. Headlines pick whichever is louder. The fix is not a bigger number, it is a wider meter. Some researchers now argue exactly that. Report both boundaries, building and grid, side by side. Until then, you can do the split yourself. One careful study already did. One query, counted twice. Remember how it split. 1 part in 8 stayed in the building. 7 parts went where the meter wasn't.